There are lots of planets out there. Um, there's nothing from the point of view of physics and chemistry that would tell you that there aren't extraterrestrial self aware beings. The philosophical or theological issues of the existence of such beings are very interesting, but I'm neither a theologian nor a philosopher. And we just don't know.
Right.
In fact, we don't know yet of any form of microbial life that formed outside of the Earth. We're still on that part of the quest. And so I think we just have to accept the fact that there's no data.
Well, welcome to the Society of Catholic Scientists podcast. I'm one of your co-hosts, Dan Keebler, and Steve Barr, my co-host, is here as well. And this is the second of two episodes that we are doing with Dr. Jonathan Lunine, who is the Chief Scientific Officer of the Jet Propulsion Lab at NASA, that's out at Caltech. And we talked to him in the first episode of our podcast, just a little bit of his scientific journey, his faith journey. But we want to talk a little bit more in this episode about his actual research and his findings, particularly how it relates to finding life on other planets. What do we do in terms of what are we looking for? What's the likelihood of that, and so forth. So, Jonathan, I know you have a textbook on astrobiology that you wrote, and so what is astrobiology? What does that entail? What's that as a discipline that might kick us off in terms of looking at the research that you do?
So astrobiology is defined as the study of the origin, distribution, and future of life in the universe. And the questions that astrobiologists try to answer are: how did life begin on the Earth? How did it evolve to what we see in the present day, together with the evolution of our own planet Earth? Is there life elsewhere in the solar system or in the cosmos beyond the solar system? And what is the future of life on Earth, including humankind? Uh, um, what is the sort of planetary destiny, I guess you could say.
Yeah.
So that broadly is what the field
Yeah.
consists of.
It's a pretty interdisciplinary field, if I'm not saying, right? Because you've got chemistry, you've got biology, you've got physics, you've got geology, you've got a lot of different disciplines that expertise from different disciplines that are going to weigh in on this subject
Right.
of life
Yeah.
on Earth and on other planets, right?
Yep. You missed astronomy and planetary science, but
Okay. Okay. Well, we assume those, given that's our guest here. So, but yeah, the a lot of times we look at life. We have to, like from a Earth centric perspective. So the life needs water. It's got maybe a carbon based chemistry, and there's actually good scientific reasons. Water has a certain properties that make it a really good solvent. Chemistry allows for a certain complex chemistry. And so as you look in the solar system and so forth, we tend to be looking for water and organic compounds, right? Usually. But what is your view on that? Do you think that that's a good way of going, or are we missing, when we do that, are we possibly missing something? Because life could arise in a different way, maybe.
Yeah. So there is this problem of how you define life, and there actually is at least one entire book written on the subject by a philosopher of science, Carol Cleland. And the issue is the following: that we have exactly one example of life.
Right.
All life on Earth is biochemically the same. Morphologically, structure, behavior, lots of variety, but it's all DNA and RNA. It's all the same basic processes. The information is in the DNA transferred by the RNA that builds the proteins. The proteins are the structure and the catalysts of life. Um, so when you try to imagine life that's based on a completely different set of chemicals, or maybe not even on chemicals at all, you really don't have enough of a power of generalization from life on Earth to be able to do very much in the way of very specific predictions. So, for example, Saturn's moon Titan, out at Saturn, very cold, water's frozen out, but methane, which is present in this dense atmosphere of nitrogen, plays the same role as water does on the Earth. It forms rain and clouds and these big seas and lakes on the surface of Titan. Well, could there be a form of life that has come to be and thrives in liquid methane and its sister molecule ethane? What would that life be like? What would be the structures, the membranes that would enclose the quote unquote biomolecules? What would be the information carrying molecule? How would structure be built? What would be the energy carrying molecules? The very clever chemists have speculated on this and made some proposals, but in the end, it's a very, very difficult problem to try to make predictions. And maybe someday we'll go to the seas of Titan and try to find something there. But for now, I think the best chance of looking for life that had a separate origin from life on Earth is really to go to Earth like environments, liquid water, even if it's underneath ice, and try to find evidence for biochemistry in these oceans of liquid water in the moons of the outer solar system, Europa and Enceladus in particular, what we call ocean worlds.
And
I have a question
what,
before we get to that. And so you're not primarily an astrobiologist, right? I mean, so your first research was presumably in planetary and science and
That's right. So I got my degree in planetary science. Astrobiology didn't exist at the time. It was
right.
called exobiology. And it was really in the mid 1990s with two discoveries. One was the first planet around a star like the sun, and the other was this Martian meteorite that at the time was thought to maybe have evidence of life in it, but probably does not. This was a rock blasted off of Mars by an asteroid impact. That kind of galvanized NASA through Vice President Al Gore at the time
Right.
to, they got more money. They created this field called astrobiology. They started an institute. And so, a rose by any other name would smell as sweet, but it's really the evolution of exobiology into something a little broader.
So as you told us in the previous part of our discussion, you were involved in a lot of probes of other
Yes.
planets and
Yeah.
moons to begin with.
Yeah.
Is that still the major thrust of your
That's
research?
that's my major thrust, and that's how I got interested in astrobiology. So, first off, late 1990s, the Galileo orbiter orbiting Jupiter. These are the missions I've been describing, by the way, I should say, are either run by or mostly run by Jet Propulsion Laboratory, which is where I work now. Kind of the center of planetary exploration, not the only place. NASA Goddard also and Applied Physics Lab do some, but these missions I've been talking about are mostly JPL missions. So the Galileo orbiter measured what are called induced magnetic fields in the vicinity of Europa, one of the moons of Jupiter. Very smooth, only a couple of craters on it, icy surface, rocky interior. That magnetic signature is best interpreted as being due to a salty liquid water ocean under the surface, where these fields are generated as Europa, actually, as the magnetic field of Jupiter passes through Europa, and that magnetic field is time variable. So physicists who take E&M or teach E&M know that from time variable magnetic fields in a conductor, you get eddy currents and induced fields. And that's what Galileo
Hmm,
found. Great.
interesting.
Cassini went to Saturn, and this tiny moon of Saturn, only 500 kilometers, 300 miles across, Enceladus, had this big plume of gas and ice pouring out of it. Again, an icy shell surrounding a rocky core. And more careful measurements by Cassini showed that there's an ocean underneath Enceladus as well. But the key to Enceladus, the thing that really got me interested because I participated in these observations, is that because this plume of ice and gas was safe enough to navigate through, Cassini was actually targeted through this plume. And because it carried instruments that can measure the composition of the ice and the gas, instruments called mass spectrometers. We now know that underneath the surface, and presumably from this ocean, there's salty water, organic carbon containing molecules, grains, tiny grains of silica, SiO2, which are a signpost of interaction, chemical interaction between rock and liquid water, presumably at the base of the ocean, generating other minerals and energy for life, and hydrogen that's a byproduct of that process. So there's an ocean that seems to have all the basic requirements for life.
That's good. So, do you think that is Enceladus is what we have the most information about that would make it
It
most
is.
likely to have life as opposed to the other
Yep.
ones we've looked at in the solar
So,
system?
right. So the Europa Ocean was discovered first in the late 90s. Enceladus 1 was a decade later. But the Galileo orbiter at Jupiter didn't have the same kind of instruments that Cassini had at Saturn. And there was no evident large plume at Europa anyway to fly through. Now, we have a spacecraft, as we're talking now, down at Cape Canaveral, attached to a rocket, a SpaceX rocket called Europa Clipper. It's a NASA mission. JPL and APL are the primary uh, uh, NASA entities that are doing that mission. And we're waiting for Hurricane Milton to pass so that this thing can be launched to Jupiter. And that will be able to make the kind of measurements at Europa that have been made at Enceladus by Cassini. And then we'll know something about whether the ocean of Europa has organic molecules in it, how salty it might be, because the Galileo measurements have a lot of uncertainty. Are there other minerals coming out? And we're depending on this heavily fractured surface being a conduit to the ocean and having material periodically coming out. And then the mass spectrometers on Europa Clipper will be able to detect that material. So if all goes well, by the beginning of the next decade, we'll have the same information on Europa that we have for Enceladus.
So there are plumes coming out of Europa, or is that something that we know, or we
Yeah,
hypothesize based on what we know about it at this point? And is that
there's circumstantial evidence. So the
okay?
famous Hubble Space Telescope, which is in orbit around the Earth and has been operating for decades, some measurements were made in the ultraviolet that show a sort of a bulb. There's a kind of a thin shell of gas of atomic oxygen and some other things, a so-called exosphere around Europa. But there's a bulge to it in the south that has been interpreted by some as perhaps being a plume. And that was
Okay.
detected from the Earth by the Hubble Space Telescope, from space, near Earth space by Hubble. That's as much as we know. Even if a plume
Yeah.
is not there, these instruments are sensitive enough that just the evaporation and sputtering due
Okay.
to radiation of molecules off the surface, those will get to the mass spectrometer.
Okay.
So I have a couple of questions. So one, if we're looking for life, it's presumably microbial life, single cell organisms, right? So how would, if it turns out, I mean, how would one ultimately go about determining if life had exists or had ever existed on Enceladus or Europa? You have
Yes.
to land something there, presumably,
Well, not
right?
necessarily. So, yeah, I should have taken a step back. When we talk about looking for life in our solar system, we're talking about looking for microbial life, single celled organisms, maybe in Europa, something a little bit more complicated. We don't know. But the reason that that's interesting is that these are places that are isolated from the Earth. So if we find biochemistry, there's a pretty good chance that it had a separate genesis from life on Earth. And that's one of the things that's very exciting. So, how do you detect life without going down into the ocean with a microscope and trying to find cells? And the answer is that you look at a number of things. You look at the pattern of organic molecules that are present. Are there amino acids present? Those are the building blocks of proteins. If they are, is the distribution of the different abundances, is the abundances of the different amino acids such that you would say that biology is going on? And here we get into sort of details of chemistry, but You can make amino acids without life. There are amino acids in meteorites. You can make them in the lab. But the pattern of the abundances that you get really depends in that case only on how easy it is to make the amino acid. The easiest amino acid to make that requires the lowest energy is the most abundant. In life on Earth, that's not the pattern we see because the ones that are easiest to form are not the most useful. So there's a different pattern of amino acids that isn't what we would call in concordance with the free energy of formation of these. If we find that same kind of pattern, we find the amino acids, first of all, and we find that same kind of pattern in the plume of Enceladus or Europa, that would be a signpost of life. We wouldn't be studying life itself. It would be a signpost of life. So the analogy I try to give people is if you've seen Jurassic Park, the first movie, the first thing that the protagonists get to see is not the Triceratops. They see Triceratops poop. That's what they come
Right.
upon first.
Right.
And there's this music about, sort of rising because, that's our first hint of a dinosaur. It's the byproducts of the dinosaur, not the dinosaur itself. And then
Yeah.
in the next scene, they're led to this, ill Triceratops that's lying on its side, and the music gets even more dramatic. So we're looking for, just if I could put it in a scatological way, we're looking for the poop. The
Or
next step,
we can say excreta.
excreta, the excreta. Thank you. We're looking for the excreta.
Yeah.
And
So
that
these
would be
the things you found so far, like on meteors, you hear about the meteor, you find amino acids. At this point, what we found is what you would find based on the thermodynamics, the things that are easiest to form, like a lot of glycine, like that. But
exactly.
you
So,
just that, so it's not
so,
indicative of life
so what would
necessarily.
you have to do to see what the amino acids were on Enceladus? How do you go
So
about
it's
that?
as simple as flying, going back to Enceladus, flying modern mass spectrometers. The ones on Cassini were 1980s technology, so very low resolution. Flying modern mass spectrometers that can detect molecules to a much more definitive way, and also to much heavier molecules. So the Cassini mass spectrometers were limited in the molecular mass, the number of atoms per molecule. And amino acids, except for the simplest ones, have what are called hundreds of Daltons. So that's, carbon is
Mm.
12 Daltons, hydrogen is one. So we're looking for molecules with lots of carbon in them. Modern mass spectrometers can do that. That's all we really need. Now, another thing about amino acids, since we're focused on them, is for all but the simplest amino acid, the structure comes in two. See if I can get my hands close together.
Yeah.
Structure comes in either a left-handed or right-handed form. Chemically, they're the same, but they're mirror
Wow.
symmetric, so that if I put my hands together like this, the thumb is on top of the thumb, but I have to reverse them. I can't put them together this
Right.
way and have the thumb lie on the thumb. So that is chiral symmetry. And all but the simplest amino acids are chiral. And in life on Earth, for good structural reasons, there is what's called enantiomeric purity. All of the amino acids, with very few exceptions, are left-handed. And to build proteins, you either have to have all left-handed or all right-handed. You can't have a
Mhm.
mixture. Sugars that are in the DNA, they're all right-handed. If you try to mix them, you don't get the DNA structure.
So
In
that would go back to
meteorites, in meteorites, you have a nearly equal combination of
I
left and
see.
right.
Okay, that's interesting.
and
Fine.
that would go back to the very origin of the first living things, or is that something the preference for one-handedness could that develop later in evolutionary history?
It had to be right at the beginning
Right at the
because
beginning.
it's
Okay.
Yeah.
it's intimately tied with how proteins are put together and how
Okay.
DNA is put together. So that preference was set right at the beginning, and
Uh-huh.
how it was set is still a great debate among origin of life people. But that requires a somewhat different instrument than a mass spectrometer, called a chromatograph, with technically a chromatograph with chiral support, either gas or liquid. That can be flown as well. If you were to go to Enceladus and find amino acids with that pattern that's not thermodynamic and is strongly left or right-handed,
Mhm.
that would be a pretty that would be a slam dunk, I would say.
Uh-huh.
for life.
That's pretty exciting.
Yeah. Yep.
And what's your take on like the methane lakes and that being, you mentioned a little bit, you'd have to be some exotic chemistry, but what's your, where do we find those again in our solar system?
That's Saturn's moon Titan. That's the only
Okay.
place. That's the
Yeah.
large moon. Also at Saturn, like Enceladus, is much larger than Enceladus. It's in fact, Titan is the size of the planet Mercury. It's 5,000 kilometers across. Um, I worked in the early when I got to Cornell in 2011. I had a grant actually from the Templeton Foundation from their Great Science Questions to study whether you could have structures in liquid methane, ethane that would have the functions of equivalent to biomolecules on the Earth. And I got a team of an organic chemist and a former particle physicist who was doing biophysics and a chemical engineer and various others. And there were people at JPL doing work also on this at the same time. It was very interesting, but it was very frustrating because, again, to two things to really have sort of guidelines as to what would constitute life in such an exotic chemical environment was very difficult. Water on the earth is so-called hydrogen bonded. It's very structured, and all biomolecules function based upon their interaction with this hydrogen bonding in water. Methane doesn't hydrogen bond at all, not at all, no structure whatsoever. So, I mean, the differences are so profound. The other problem is that things don't dissolve very well in liquid methane and liquid ethane, and that's another problem. So, yeah, I mean, we've tried to tackle it. Others have tried to tackle this question. It's a real daunting one.
Yeah.
So the betting is a bet. If one were to figure out where to put one's resources in looking for life, it's probably water-based, carbon-based, things like that. Though other things might be possible, but
Yep.
that's where you put the money, right?
That's what I would say. Yeah, that's right.
Yeah.
Absolutely.
So
So
outside of
do you,
our solar system, what's the likelihood, when you look outside of our solar system of finding like exoplanets that fall into that category that might be ones that
Right.
could have life, rocky planets that meet some of those criteria? Are they, how abundant are they? And what's your take on that?
Right. So that's not known yet, but we're on the cusp of knowing that. So one of the things that over the last 30 years, since the first discovery of an exoplanet around a star like the sun, has become more and more evident with better and better kinds of telescopes is that planets are incredibly common. For every star in our galaxy, there's on average a planet, and most of these are in multiple planet systems. Now, whether they're habitable requires analyzing the light from their atmospheres, the spectra of these planets, and that's much more difficult to do. But Hubble started doing that with big planets, gas giants. James Webb Space Telescope, which was launched a few years ago, is doing that now with planets that are a little bit larger than the Earth. And so far, nothing there with an atmosphere for a rocky planet, nothing with an atmosphere that has carbon dioxide and so on seems to have popped up. But there's somewhat bigger objects that might be sort of in between the size of the Earth and Neptune that have some interesting things in their spectra. The next step is something called the Habitable Worlds Observatory. Actually, there's a step before that, I should say. The Nancy Roman telescope, which will be launched in a couple of years, may be able to do a somewhat better job than James Webb Space Telescope. And then for the next decade, probably mid to late part of the 2030s, the next step beyond James Webb, the Habitable Worlds Telescope, will really be able to tell us what kind of molecules are in the atmospheres of Earth-sized planets around other stars, and then we'll really know what the fraction of habitable planets is.
but based on what we know now, it's seen that the fraction of habitable planets that are habitable is substantial, or it's not something that's
We
exponentially
just
small.
we don't really know enough yet, and the
Okay.
problem is that um, to be able to detect the atmospheres or any signature of an Earth-sized planet, JWST has to be looking at stars much smaller than the sun, so-called
Right.
red dwarfs. So these are planets very close to their parent stars, tidally locked. And so far, we haven't seen anything really in that kind of class of planets with a convincing atmosphere. There may be some, but it's very different from our solar system. Um, so, we're just kind of at the edge of being able, I should say, astronomers are at the edge of being able to answer that question. And there may be some, a few gems that come from JWST, from Webb. But I think the real survey of that is going to be with Nancy Roman and then the Habitable Worlds telescopes.
Since we're getting sort of towards the end of our interview, I feel that we should ask you, since this is probably a burning question for many people. So, do you think it's plausible that there could be just advanced extraterrestrial life out there, um, and that A, and B, how plausible is it that either they have visited Earth or ever will visit Earth? What are your thoughts on that?
So what I tell people is that I have no more knowledge about this than they do. That there's nothing in my own field of science that gives me any guidance on that. There are lots of planets out there. There's nothing from the point of view of physics and chemistry that would tell you that there aren't extraterrestrial self-aware beings. The philosophical or theological issues of the existence of such beings are very interesting, but I'm neither a theologian nor a philosopher. And we just don't know.
Right.
In fact, we don't know yet of any form of microbial life that formed outside of the Earth. We're still on that part of the quest. And so I think we just have to accept the fact that there's no data. I mean, if
Right.
we, SETI, the search for extraterrestrial intelligence using radio telescopes, has been searching with ever increasing sensitivity and coverage and frequency range. Nothing convincing has shown up. But if you think about the age of the galaxy, 13.8 billion years, maybe life could begin after the first few billion years or 5 billion years. So there's something like 10 billion years there. And how long does it take sophisticated intelligent life to arise? It took 4.5 billion years on the Earth. Maybe it takes 10 billion years on average. Maybe it takes only 2 billion. But if that life doesn't itself exist in the form of a communicable civilization for millions or billions of years, the chance that we have an overlap is very small. And so
Yeah.
there could be such things, but our
The
chance of
chance that
overlapping is small.
our contemporaries
Yeah,
is much smaller than
exactly.
the chance that they exist.
Exactly.
Yeah, there seems to be so many probabilities that we don't, even just a life on our planet, we don't even really understand how. We have some ideas, but we don't really, can't say, oh, this is the probability even on our
Uh,
planet that the life
Actually,
evolved or emerged. What had to have happened,
yeah, the first textbook I wrote, Earth Evolution of a Habitable World, was the evolution of the Earth from the planetary science perspective. And the twists and turns of the history of the Earth are so intricate that it makes it very difficult to predict whether any particular planet anywhere else is going to be habitable long enough for intelligent life to arise.
Yeah. Yeah, we just ask you if you had unlimited resources in terms of a mission that you could put together for NASA. I don't want to get you into trouble here of suggesting something what would you want to do? You think, well, this would be a great mission to in our solar system that we could really get some good data if we put these instruments on this probe and went to this place. Yeah, what's your sort of
So
thought there?
I would go to Enceladus.
Right.
I would go back there with the instruments needed to detect life. And if I had an infinite amount of resources or a large amount, I don't need an infinite amount, I'd put a lander on the surface with very sophisticated instruments. And um, I would look for life coming out of the surface of Enceladus in the form of the plume.
Thank you for coming on the podcast, and this has been a lot of fun. I'd like to have you back at some point to talk more about extraterrestrial life, and maybe also about something that you know a lot about, Father Georges Lemaitre and
Yep.
the priest who proposed the Big Bang theory. I think that would be an interesting thing for us to talk about in a future episode. But
I'd love to do that. Yep,
well,
absolutely.
thank you for today. Anyway,
Thank you, Dan. Thank you, Steve. It's been a pleasure. Looking forward to it again. Bye bye.
okay, great.
Thanks for listening to this episode of the Catholic Scientist Podcast, sponsored by the Society of Catholic Scientists. If you enjoyed this episode, please consider subscribing. And you can also show your support by donating to the Society to help us produce content like you just heard. You can donate by going to our website at catholicscientist.org and clicking on the donate button. You can also find other useful resources, articles, and videos on our website.